Hello. In this video we are going to see how to study the variation of certain logarithmic functions. In this example we have, in part A, we have given this function g defined over 0 plus infinity by g of x, which is equal to 1 minus x squared minus ln x. So we need to study the variations of the function g. Variations means when this function is increasing, when this function is decreasing. Now, in order to determine the variation of any given function, we need to study the sign of its derivative. So let us find the derivative of g. So what is g prime here? G prime of x. G prime of x is equal to, so 1 is a constant, its derivative is 0, minus derivative of x squared is 2x, minus the derivative of ln x, it is 1 over x. So this is equal, common denominator here, so this is over 1, so it's minus 2x squared minus 1 all over x, which is equal to minus into 2x squared plus 1 over x. Now, we know that x is positive. So x is positive, 2x squared is positive, adding 1 to 2x squared it's positive. So the whole numerator is positive times this minus, it's negative, over positive, so the whole g prime will be strictly negative for all x in the domain which is 0 plus infinity. So if I set the table of variation of this function, we get this is x, this is g prime, this is g. So the domain is 0 plus infinity, g prime always negative, so the function g is always decreasing. So decreasing from where to where? So I need to find these values here. In order to find these values here, first I have to find the limit as x approach 0 of g of x, which will be equal to 1 minus 0 squared minus ln 0, which is minus infinity, right? So it's minus of minus infinity, so my answer will be plus infinity. Now the limit, so from here we can deduce that x equals 0 is a vertical asymptote. X equals 0, vertical asymptote. Now, limit as x approach plus infinity, as x approach plus infinity of g of x is going to be equal to 1 minus into plus infinity, because x squared will be plus infinity, minus into plus infinity also because ln x goes to plus infinity as x approach plus infinity, so we get minus infinity, which is minus infinity. So back to the table of variation, we know now that at 0 we have vertical asymptote, so we should draw this shape here. So at 0 it's plus infinity, and at plus infinity it's minus infinity. So this is the variation of the function g. Now we have to calculate g of 1. How to calculate g of 1? So simply we substitute, instead of x 1 in g of x. So g of 1, it's going to be equal to 1 minus 1 square minus ln 1. So this will be 1 minus 1 square, which is 1, minus ln 1, which is 0. So we get 1 minus 1, which is 0. So g of 1 is 0. So it means if x is 1, g of 1 is going to be 0. Okay? Now they say deduce the sign of a g. To deduce the sign of a g, we are going to use the table of variation, either the table of variation, or if we draw the graph of g, we may deduce it from the graph of g. But the table of variation is enough. As you can see here, for all x's between 0 and 1, here it means whenever we have x between these two values, 0 and 1, we can see that our function decreases from plus infinity till 0, which means it is above the x-axis. The graph is above the x-axis. It means our function g is positive whenever x is between 0 and 1. So we can write for x, or g of x is positive if and only if x is between 0 and 1. Whereas for all x greater than 1, we have the graph is decreasing from 0 till minus infinity. Decreasing from 0 till minus infinity, it means it is negative. So we say g of x is negative if and only if x is greater than 1. So this is the sign of g of x. Now if I put g of x is greater than or equal to 0, it may be equal to 0 whenever x is equal to 1. So this is it. This is part A. Let's go to part B. We have in part B, f be the function defined over 0 plus infinity by f of x, which is ln x over x plus 2 minus x. Question 1 is to determine the limit of f of x as x approach 0 plus. So let us start. Limit as x approach 0 plus of f of x is equal to limit as x approach 0 plus of ln x over x plus 2 minus x, which is equal. Ln x as x approach 0 plus is minus infinity over x, it is 0 plus 2 minus 0. So this is equal minus infinity over 0 plus, which is minus infinity, plus 2 minus 0, it's plus 2. So minus infinity plus 2, which is minus infinity. If I want to specify here the asymptote, since as x approach 0 plus the answer is infinity, it means we have x equals 0 vertical asymptote. Now the limit as x approach plus infinity, limit as x approach plus infinity of f of x, it is the limit as x approach plus infinity of ln x over x plus 2 minus x. So we have a rule that says ln x over x as x approach plus infinity is 0. So this is a property for ln x. So this is approach 0. So we get 2 minus of plus infinity. So this will be equal minus infinity. So the second part, we have part 2, verify that f prime of x is equal to g of x over x squared. As you recall, g of x is our function in the first part, which was g of x, which is equal to 1 minus x squared minus ln x. So let us prove this. In order to prove that f prime of x equal g of x over x squared, I should start by finding f prime. What is f prime? It means I have to derivate the function f. So as we can see here, if we go back to our function f of x, the function f of x is given by ln x over x plus 2 minus x. So we have to derivate ln x over x using the rule u over v. The derivative of u over v, which is u prime v minus v prime u over v squared. So that's what we are going to apply for ln x over x. So u prime, so let us write. So I'm going to recall it here. If we have function of the form u over v and I want to derivate it, it's going to be equal u prime times v minus v prime times u over v squared. So u prime, so let me recall what is f of x here. F of x equal ln x over x plus 2 minus x. So this is u and this is v. So u prime, it means it is 1 over x times v which is x, minus v prime, which is 1 because the derivative of 1 is derivative of x is 1, times u, which is ln x, all over v squared, which means x squared, plus derivative of 2, it is 0 since the derivative of a constant is 0, minus derivative of x, it is 1. So let us simplify. We get this is x squared. So here we have x and x cancelled. We get 1 minus 1 times ln x, which is ln x. 0 minus 1, it is minus 1. So if I continue this to make common denominator here, we get common denominator x squared. So it is 1 minus ln x. Here we should multiply by x squared and here by x squared. So we get minus x squared. As you can notice here, this function 1 minus ln x minus x squared is simply g of x. So this is g of x over x squared. So that's what we have to prove, and we prove it. Now they say construct the table of variation of f. So as you can see here, since f prime equal g of x over x squared, we can deduce that f prime, the sign of f prime and the sign of g are the same, because x squared is always positive. So what will be the sign of g of x? It will be for f prime. So we recall that the sign of g, according to part capital A, was g of x was negative whenever, let us recall part A. So g of x was positive whenever x between 0 and 1, and negative for x greater than 1, and 0 at 1. So we are going to draw the table of variation for f of x using that of g of x, using the sign of g of x. So if I draw the table of variation, this is x, this is f prime, and this is f. So the domain for f, which is 0 plus infinity, g of x changes sign at 1, so f prime will do the same thing. G of x is equal to 0 at 1, it means f prime is equal to 0 at 1. So g of x was negative between, or positive between 0 and 1, so f prime will be positive between 0 and 1, and negative for x greater than 1. So we have at 0 vertical asymptote, so we draw this ladder shape. So f will increase, then decrease. Increase, we have seen as x approached 0, the answer was, the limit was minus infinity. So let's set this on the table. So as x approach 0, f will approach minus infinity, and as x approach plus infinity, the answer was also minus infinity. Now at this point here, this point is a maximum. So in order to find this maximum, we have to find f of 1. This is equal ln 1 over 1 plus 2 minus 1, which means the answer is 1, because ln 1 is 0. So 2 minus 1 equals 1. So we have the maximum, it is 1, 1. Okay? So this is the table of variation of f of x. Let's go now to part 3. What do we have in part 3? In part 3 we have prove that the equation of x equals 0 has two distinct roots, alpha and beta, where alpha in the interval 0.4, 0.5 and beta between 2.3 and 2.4. In order to prove this, we're going to use what is known as the intermediate value theorem. Intermediate value theorem says that first, f is a continuous function. F is a continuous function, and we have f of 0.4 is equal to ln 0.4 over 0.4 plus 2 minus 0.4, which is equal, if I calculate this using a calculator, we are going to get, so ln 0.4 divided by 0.4 plus 2 minus 0.4 equals minus 0.69, which is negative. If I calculate f of 0.5 now, we're going to get ln 0.5 over 0.5 plus 2 minus 0.5. Let's see what we get. So this is ln 0.5 divided by 0.5 equals plus 2 minus 0.5, which is 0.11, which is positive. We can deduce from these that then f of x equals 0 admits at least one solution in the interval 0.4, 0.5. But if we look for the table of variation of f, we can see that within the interval 0.4, 0.5, which is basically here, 0.4, 0.5, and this part of the domain, the function is strictly increasing over this part of the domain. Okay, so since it is strictly increasing over this part of the domain, it means this solution is a unique solution. This alpha within this interval is unique. It's the only one. Okay, so but using the table of variations of f, f is strictly increasing within this interval, Hence, f of x equals 0 admits a unique solution alpha in the interval 0.4, 0.5. We will do the same thing for the second interval. We will say f is continuous and f of 2.3. So f is continuous and f of 2.3, it's going to be equal to ln 2.3 over 2.3 plus 2 minus 2.3. So let me calculate it. We got, so ln 2.3 divided by 2.3 equals plus 2 minus 2.3, which is equal to 0.06, 0.06, which is positive, and f of 2.4, which should be negative. So if I calculate f of 2.4, it's going to be ln 2.4 divided by 2.4 equals plus 2 minus 2.4, which is minus 0.035, minus 0.035, which is negative. Hence, from this, we say f of x equals 0 admits at least one solution in the interval 2.3, 2.4, but f is strictly, let me check here, strictly, so the interval 2.4, 2.3, 2.4 is here. So within this interval it's strictly decreasing. So within this interval it's strictly decreasing. So however, f is strictly decreasing over this interval. Hence, this solution beta is unique. Okay, so this was part 3 for this question. Let's go now for part 4. In part 4, what do we have? In part 4, we have to prove that the line D of equation y equal minus x plus 2 is an oblique asymptote to C, the representative curve of f. How to prove the line D is an oblique asymptote? So, to prove we have oblique asymptote at y equal minus x plus 2, we have to prove that we have to show that limit as x approach plus infinity of f of x minus y is equal to 0. That's what we have to prove. Y for D, for the oblique. Okay, that's what we have to prove. So let us find this limit. In fact, the limit as x approach plus infinity of f of x minus y is equal limit as x approach plus infinity f of x, which is ln x over x plus 2 minus x minus y. Y for the oblique asymptote is minus x plus 2. So minus x plus 2. So this is equal limit as x approach plus infinity of ln x over x plus 2 minus x, minus times minus, it's plus x minus 2. So this is equal, so plus 2 minus 2 cancelled, minus x plus x cancelled, so it's the limit as x approach plus infinity of ln x over x, which is using the property of limit of ln, limit as x approach plus infinity of ln x over x is 0. Therefore, the line D of equation y equal minus x plus 2 is an oblique asymptote. Then they say study the relative position of C and D. Relative position, it means which curve is above the other. The curve C, which is for the function f, or the line D, which is for with this equation y equal minus x plus 2. In order to determine which curve is above the other, we have to find f of x minus y without limit now. So we have to study the sign of f of x minus y of the oblique. So f of x minus y, we get the final answer is ln x over x. So this is f of x minus y, it's ln x over x. So let us, in order to study its sign, let us first solve it equal to 0 to see where it will be 0. So this means the numerator is 0, ln x is 0. Instead of 0 we put ln 1. So this means x is equal to 1. So here at this abscissa at x equal 1, both curves intersect. Now in order to know the sign of f of x minus y, let us put here, this is x and this is f of x minus y. F of x minus y, we have the domain first here, it's 0 plus infinity. F of x minus y, it is 0 at 1, so it will be 0 here. It means the two curves intersect here. I may write here C intersect D. Now between 0 and 1, we know between 0 and 1 ln x is negative. You may try value. I may choose between 0 and 1 0.5. If I substitute here 0.5, ln 0.5, and I calculate it using a calculator, ln 0.5 it's a negative value, so over 0.5 it will remain negative value. For greater than 1, any value, if I give x any value greater than 1, 2 for example, ln 2 it's a positive value, ln 2 over 2 it's a positive value, so this is positive. So here negative means C below D, this side C above D. So this is a relative position between C and D. Let's go now for the last part. In the last part we have to draw the graph of D and C. In order to draw the graph of D and C, we need the table of variation. Okay, so in the table of variation we have our curve starts from minus infinity of the vertical asymptote, right? Then it goes up to the maximum point, and goes down to minus infinity. As we proved later, we proved that we have oblique asymptote here, y equal minus x plus 2. So our function will go to minus infinity of the oblique asymptote. So in order to draw the graph for f, I need first to draw the asymptotes. To draw the asymptotes, so we have two asymptotes, x equals 0, which is the vertical asymptote, and y equal minus x plus 2, which is the oblique. In order to draw the oblique, we need to take 2 points on this oblique. I draw this table, this is x, this is y, and I start to give values for x and find the respective values for y. If I take, for example, x equals 0, if I substitute 0 instead of x, we get 0 plus 2, which is 2. Now let us give y the value 0. If I substitute instead of y 0 and find x, we can find that x will be also 2, right? So let me write it here. If x is 0, y will be equal to minus 0 plus 2, which is 2. And if I give y equal 0, we have 0 equal minus x plus 2. And to find x, we take x to the left side, so x will be equal to 2. So these 2 points, we plot these 2 points in order to draw the graph of the oblique. So let me draw the graph here. Okay, let us draw it here. So we have vertical asymptote x equals 0. It means the y-axis is the vertical asymptote. Okay, so this is the vertical asymptote. We draw it as dotted line. Okay, so this is the dotted line. This is x equals 0, which is the y-axis, and this is the x-axis. So this is O. Now I have to plot the 2 points, which are 0, 2 and 2, 0. 0, 2, the first point 0, 2. This is, let's suppose this is 1 and this is 2. This is 0, 2. This is the first point. The second point is 2, 0. This is 1, 2. This is 2, 0. I join these 2 points. These represent the oblique asymptote. Okay, so joining these 2 points, we get the oblique asymptote. Okay, of course, use a ruler when you are drawing. Anyway, if now I have to draw the maximum point, which is 1, 1. The maximum point 1, 1, it should be on the oblique. Okay, 1, 1 is going to be on the oblique. So I'll repeat this graph. So the graph, this is the vertical, this is the vertical line, which is the oblique, the vertical asymptote, and this is the x-axis. So the oblique passes through 2 points, which are 2, 0 and 0, 2. So this is the oblique. The oblique, we have to make it dotted also. So this is no. Okay. So let me draw. This is the oblique. So this is the oblique asymptote. If I take this is 1, 1, 1, 1, this is 1, and this is 1, so 1, 1 should be on the oblique. This is the maximum. Now to draw the graph, we know that the graph, according to the table of variation, the graph will start from minus infinity of the vertical, will start from here, goes to the maximum. So if I go to the graph, we have to go from minus infinity of the vertical, go up till, go up to the maximum. Now notice here that using the table of relative position between C and D, so C is below D between 0 and 1. For all x between 0 and 1, C is below the asymptote, whereas after the 1 it becomes C above the asymptote. So let us draw according to this. So before 1, so this is the 1, this is 1. So before 1, C below the oblique, and after 1 it's going to be above the oblique. And now from the maximum it goes to minus infinity of the oblique. Okay, so this is the curve. Now of course the graph is not that much clear here because I can't draw easily on the laptop. So let me show you the graph using GeoGebra. If we draw the graph here on GeoGebra, we are going to see that our function is going to be of this shape, and this is the oblique, okay, and this is the maximum. The maximum is at 1, 1. So this is the graph. I guess here it's more clear. Okay, so this is our graph, and as you can see here, this is the first point here is with abscissa alpha. Alpha was between 0.4 and 0.5. This is alpha. So this is the first x-intercept, and this is the second x-intercept between 2.4 and 2.5. So points are here first. This is A with abscissa alpha and B with abscissa beta. Okay, I guess now the graph is more clear. Thank you. See you in the next video.